Modern large language models can produce what looks like a flawless logical proof. They can list premises, apply recognized rules, and output a highly persuasive conclusion. Engineers often try to enforce accuracy using stepwise prompting or self-consistency polling. The expectation is that if a model is forced to show its work, the underlying logic is sound. But a sequence that simply looks like a valid derivation doesn't guarantee the conclusion was constrained by the active premises. Predicting the next highly probable token is statistical pattern completion. True deductive reasoning requires logical entailment, the condition where, if the premises are verified, the conclusion follows by absolute necessity. In high-consequence environments like access control or safety systems, a convincing text sequence is a liability if the logical lineage is broken. Even when provided with retrieved facts and explicit rules, language models fail in specific, predictable ways. Take premise mutation. A model might read "usually causes" in the prompt, but silently drop the word "usually" by the time it reaches the conclusion. The logical force shifts entirely, yet the system validates the step. Then there is unstated premise importation. The model pulls in a generalized assumption from its training data that was never declared in the active facts, treating it as verified evidence. And when confronted with an active operational defeater, the system often exhibits exception blindness. It accurately cites the standard rule while failing to notice the specific emergency exception blocking it. Real institutions avoid these errors by governing rules through specific jurisdictional authorities, limited scopes, and version controls. Without a mechanism to actively block these failures, AI systems lack the precision required for permission-aware actions. To prevent these logical slips, we have to move beyond simple text generation. We need an architecture that treats deduction as a state-governed transition process. This starts with defining inferential force, the actual capacity of a premise or rule to authorize a conclusion. This force is managed through the deductive state equation. Omega formalizes the entire context required to license a logical transition, capturing the variables that language models typically lose. P represents the active premise set. Facts, working hypotheses, and assumptions are tracked as distinct governed objects. R and C stand for rules and conditions. Here, a rule acts as a scoped transition license. It only triggers when the specific parameters of the current domain are met. E is for exceptions. This allows for non-monotonic reasoning, where a normally valid conclusion is explicitly blocked if a new defeater or countercondition appears. A captures authority. A derivation requires institutional authorization, a clear link to a legitimate source before it can govern an action. Finally, D is the dependency lineage. Every conclusion is stored with a permanent, auditable trace connecting it back to the specific premises that gave it force. This structure ensures that every step forward is earned by the state of the variables, independent of linguistic probability. Operationally, the omega equation functions as an entailment gate. As the system proposes a logical step, a data orb hits the gate. The barrier only opens when it aligns perfectly with the active state. If a definition shifts or an exception is active, the gate stops the process. In this environment, failing to conclude is a valid result. If the premises are insufficient, the system safely halts. This gating architecture connects formal logical validity directly to the security requirements of real-world institutions. We can see this in action with a high-stakes decision, authorizing a contractor payment release. The facts are simple. A project manager reports a milestone is complete. However, the rules state that only a designated officer can authorize payment, unless an emergency finance director override is present. A standard language model often prioritizes a reasonable-sounding narrative. It sees the report of work being done and concludes the payment should be released. But the models silently bypass the authority node and fail to check for the missing signature. The energetic framework processes these same inputs with structural rigor. It registers the manager's report as evidence of completion, but the authority check immediately flags that the manager lacks the power to authorize a payment. The system then queries the exception state, searching for the finance director's emergency override. It returns a null result. The entailment gate remains closed. Instead of guessing, the system identifies exactly what is required to make the transition valid: a designated officer's signature or a recorded emergency approval. This prevents the AI from executing an unauthorized financial transaction based purely on the persuasiveness of the manager's report. By treating premises as governed objects, the architecture ensures that logical force only reaches the conclusion through authorized channels. Managing these states at scale requires an architecture with specialized modules for premise registration, exception monitoring, and gating. This is critical because operational facts are constantly in flux. Rules update, and evidence can expire. When this happens, the repair manager uses the dependency lineage to perform localized updates. If a foundational premise, like a regional policy, expires, the system doesn't need to rebuild every argument from scratch. It follows the lineage graph and retracts only the affected nodes. This precision keeps the rest of the system's verified conclusions active and secure. Language models, by contrast, lack the structural memory to isolate changes this way. Localized repair ensures structurally controlled AI remains auditable and efficient, even as underlying data evolves. Generating plausible text is fundamentally different from preserving the structural path of a problem. Under this framework, logical validity is a property of lineage. It cannot be earned through rhetoric. If a fact is uncertain or a premise is missing, that conditionality remains attached to the output. It cannot disappear into the final assertion. This transition from unconstrained text generation to structural control is the necessary path for autonomous enterprise and legal workflows. True autonomy relies on systems that can prove exactly why a conclusion is justified, and exactly when it has lost its force. Deductive reliability is only achieved when the system governs the explicit transfer of inferential force at every step.